In this activity, I'm going to do two videos. The first one is going to be on just limits and some definitions and concepts, and then the second one I will do some examples or some math working with strategies on how to calculate limits. So the first thing is we'll look at limits in the definition of a limit. So if you know that the limit as x approaches some number a of a function f at x equals L, so we get a value, a number there, this implies that as x gets closer and closer to a, so as x approaches the value a, the function itself, when you sub the numbers in, is approaching a limiting value of L. So as x gets closer and closer to a, the y values or the function is getting closer and closer and closer to this number L. We looked at that in the last activity when we were doing limit investigations. Our sequences and our functions sometimes were heading towards a limiting value or a limiting number, and we could see that. So the first concept with limits is if your function f at x is determinable at whatever a is, and that just means you can sub a into f at x and get an answer, then the limit is simply f at a, or what you get when you sub a into f. Now we're going to look at some properties and some laws that will allow us to calculate limits. Now, we're not going to do a lot of thinking about these properties when we're doing the math, but they do exist and they are there for us to work with. So the first property is constant. If you have the limit as x approaches a of a constant, and I'm going to use c for constant. Remember, a constant function means that there's no variable. So f at x equal to 5 is an example of a constant function. Because the function is constant, and no matter what we put in for x, our answer is always going to be 5, it doesn't matter what a we're approaching here. Any a is always going to equal this c, therefore any limit will also be c. So the limit of a constant is just whatever that number is. The next one we'll look at is what is the limit as x approaches a of x. This means the function we're looking at is simply f at x equals x. So no matter what I sub in here, that's going to be my answer. So f at 1 would equal 1. F at 2 would equal 2. F at root 3 would equal root 3. F at negative 4 would be negative 4. So no matter what a is, if I sub it in for x, that's going to be my limit, because that's what the value will be. Now we're going to look at a few laws that are based on two things. So if you have a function, we're going to call this one f at x, and we know that as x approaches a, the limit of this function f at x is some number L, and we also have a second function. We're going to call this one g at x, so we can keep them separate. And we know that the limit as x approaches a of this function g at x is some value. I'm going to call it m. Then we have a whole bunch of things that we can do. The first one says if you have a new function or a composition of function, which is f at x plus g at x, so if I'm looking for the limit as x approaches a of f at x plus g at x, I don't have to add these first and get a new function. If I know the limit as x approaches a f at x is L, and the limit as x approaches a g at x is m, and it's adding here, that means I would add my answer. This is also true for subtraction. So if I have a composition function, which is the subtraction of two functions, and I know that the limit as of f at x as x approaches a is L, similarly, I know the limit for g at x, it's m. If it's subtracting in here, I can simply subtract my answers. Multiplication and division work as well. So limit x approaches a, f at x times g at x would be simply the answer for f at x, which is L, times the answer for g at x, which is m. And this holds true also for division. If I have a composition function that's f at x over g at x, and I'm looking for the limit, I can do the limit separately and just divide my answers. So we already know that the limit of f is L, the limit of g is m. The only condition for this one is because m represents a division, m can't be 0. Now, the properties of adding, subtracting, multiplying, and dividing work, but we're not going to think about them all the time. They're just going to happen because if we look at an example of the limit of x approaches 2 of negative 2x squared plus 3x minus 1, I've really used all of the properties here except for the dividing one. I have addition and subtraction of functions. I have a constant piece. I have this piece, which is a multiplication between 3 and x. And I have this piece, which is a multiplication between negative 2 and x squared. So now, this is x equal to 2 is determinable. There's no problem with putting 2 into here and getting an answer. So I'm going to do that. It's really all of my properties, the adding, subtracting, and multiplying that allow me to do that because it says I can look at all the pieces separately. We're not going to write it all out and split it up and say that this is the limit as x approaches 2 of negative 2 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3 times the limit as x approaches 2 of x, subtract the limit as x approaches 2 of 1. But that's what's happening. Those are all of our laws in place. We're simply going to say, because this is a limit and we can add and subtract and multiply, I can just add and subtract and multiply according to all the pieces. And because 2 is a determinable value, I just put it in. So this is going to give me negative 8 plus 6 minus 1, which is going to give me negative 1 as my limit.